Have you ever wondered how the apps you use every day manage to handle enormous amounts of data so quickly, so reliably, and so efficiently? Whether it is a music streaming service like Spotify, processing your audio on the fly, a search engine ranking millions of results in milliseconds, or a data pipeline at a bank validating and loading thousands of transactions every second, there is a clever design principle working quietly behind the scenes. That principle is called the pipe and filter architecture. In this video, we are going to break this concept down in a simple, easy-to-understand way. We will explore what it is, how it works, where it is used in the real world, and why software engineers love it. Whether you are a student just stepping into the world of software, an IT professional looking to sharpen your skills, or simply a curious person who wants to understand how modern systems are built, this video is for you. So, let us dive in. Before we talk about software, let us think about something much more familiar: a water treatment plant. Imagine dirty river water entering a facility. It does not come out clean instantly. Instead, it passes through a series of stages, one after another. First, large debris is filtered out. Then, chemicals are added to remove bacteria. After that, the water goes through a fine filtration membrane. Finally, it is tested for quality before being sent to your tap. Each of these stages does one specific job. Each stage receives water from the previous step, does its work, and passes the result to the next stage. None of these steps knows or cares about what happens before or after it. They each just focus on their one task. That, in essence, is the pipe and filter architecture. In software, instead of water, we have data. Instead of physical stages, we have software components called filters. And instead of pipes carrying water, we have digital pipes that carry data from one filter to the next. Simple idea, powerful results. Now that we have the big picture, let us look at the building blocks that make up this architecture. The filter. A filter is a processing component. It takes some data as input, does something useful with it, like transforming it, cleaning it, validating it, or enriching it, and then produces an output. The most important thing about a filter is that it is completely independent. It does not know where the data came from, and it does not know where the data is going. It simply does its job and passes the result along. The pipe. A pipe is the channel that connects one filter to the next. Think of it as a data highway. It takes the output from one filter and delivers it as the input to the next filter. The pipe does not modify the data in any way. It just transports it. The source. The source is where the data originates. It could be a file sitting on a disk, a live feed coming from a sensor, a database, or even keyboard input from a user. The source is the starting point of the entire pipeline. The sink. The sink is the final destination. It is where the processed data ends up. That might be a database, a file, a screen, or a message sent to another system. The sink represents the end of the pipeline. So the complete picture looks like this. Data flows from the source through a series of filters connected by pipes and finally arrives at the sink. Each filter transforms the data in some way, and by the time it reaches the sink, it has been fully processed. Let us bring this to life with a real-world example that almost everyone can relate to: your email inbox. Every single day, billions of emails are sent around the world. When an email arrives at a mail server, it does not just drop straight into your inbox. It passes through a carefully designed pipeline of filters, each performing a specific job. Here is what that pipeline might look like. The first filter is the spam detector. It examines the email and checks for signs of junk mail, things like suspicious sender addresses, known spam keywords, or unusual formatting patterns. If the email looks like spam, it gets flagged or discarded. If it passes, it moves on. The second filter is the virus and malware scanner. It inspects any attachments or links in the email. If a virus is detected, the email is quarantined. If it is safe, it continues down the pipeline. The third filter is the content formatter. It makes sure the email is properly formatted for your email client. It might convert certain encoding types, render HTML content correctly, or resize large images. The fourth and final filter is the delivery sorter. Based on your rules and preferences, it decides whether this email goes into your primary inbox, a specific folder, or perhaps your promotions tab. Notice how clean this design is. Each filter has a single, well-defined responsibility. You could replace the spam detector with a better one without touching the virus scanner. You could add a new filter for language translation between any two existing steps without breaking anything else. That is the real power of this architecture. Here is another example, and this one is where the pipe and filter architecture literally gets its name from. The UNIX command line. The UNIX operating system was designed in the early 1970s at Bell Labs. One of its founding ideas was that each program should do one thing and do it well, and that programs should be able to pass their output to other programs as input. This is done using the pipe symbol, which is simply a vertical bar on your keyboard. Imagine you have a large log file and you want to find all lines that mention the word error. Sort them alphabetically and count how many unique error messages there are. In a Unix terminal, you can write a single line that chains together small programs, just like assembling a pipeline. The first program reads the file and passes all lines onward. The second program filters and keeps only lines containing the word error. The third program sorts those lines. The fourth program removes duplicates. The final program counts how many results remain. Each of those small programs is a filter. Each pipe character between them is, quite literally, a pipe. The data flows through each step, gets transformed, and emerges as a final clean result. This is perhaps the most direct and visible example of pipe and filter architecture in action. Let us look at one more real-world example that is incredibly common in the business world today: the ETL pipeline. ETL stands for extract, transform, and load. It is the backbone of how companies move and prepare data for reporting and analysis. Imagine a large retail company. Every day, they collect sales data from hundreds of stores around the world. This raw data arrives in different formats, with different currencies, different date formats, and sometimes missing or incorrect values. The ETL pipeline processes this data in stages, just like our pipe and filter model. The first filter extracts the data. It pulls raw sales records from all the different store databases and passes them into the pipeline. The second filter cleans the data. It removes duplicate records, fills in missing values, standardizes currency formats, and corrects any errors. This is sometimes called the data cleansing step. The third filter transforms the data. It converts currencies into a single standard, unifies date formats, and restructures the records into a consistent layout. The fourth filter validates the data. It runs checks to ensure that every record meets the required standards before it moves on. Finally, the last filter loads the clean, validated, transformed data into a central data warehouse where business analysts can run reports and make decisions. Tools like Apache Kafka, Apache Spark, Apache NiFi, and AWS Data Pipeline are all built around this exact pattern. They are used by companies like Netflix, Uber, LinkedIn, and thousands of others every single day. By now, you can probably see why engineers love this pattern. Let us go through the key advantages one by one. Modularity. Because every filter is an independent component, you can build, test, and understand each one in isolation. This makes the system much easier to develop and maintain. If something goes wrong, you know exactly which filter to look at. Reusability. A filter you build for one pipeline can often be reused in a completely different pipeline. For example, a filter that validates email addresses could be used in a customer registration pipeline, a marketing email pipeline, or a user analytics pipeline without any changes. Flexibility. Need to add a new step to your process? Just insert a new filter. Need to change the order of operations? Rearrange the filters. Want to try a different approach for one step? Swap out a single filter. None of these changes require you to touch any other part of the system. Scalability. If one particular filter is slow and becomes a bottleneck, meaning it cannot keep up with the speed of incoming data, you can simply run multiple copies of that filter in parallel. You do not need to scale the entire system, just the part that needs it. Testability. Because each filter does one thing and receives a clear input and produces a clear output, you can test each filter independently with simple test cases. This makes quality assurance significantly easier. No architecture is perfect for every situation, and the pipe and filter pattern is no exception. Let us be honest about its limitations. not ideal for interactive systems. This pattern works best when data flows in one direction. It is not well suited for systems that require a lot of back and forth interaction between components, like a chat application or a complex user interface, where actions trigger reactions in multiple directions. Overhead, head between filters. Every time data passes from one filter to the next, there is a small cost involved. The data needs to be packaged up, passed through the pipe, and then unpacked by the next filter. If you have a very long chain of filters and extremely high speed requirements, this overhead can add up. Debugging can be tricky. When something goes wrong somewhere in the middle of a long pipeline, finding the exact filter that caused the problem can be challenging. Good logging and monitoring at each stage are essential to make troubleshooting manageable. Shared state is difficult. Since filters are designed to be independent of each other, sharing information between them is not straightforward. If multiple filters need to access and update the same piece of shared data simultaneously, this pattern may not be the best choice on its own. So when should you reach for the pipe and filter pattern? This architecture is an excellent choice whenever you are building a system that needs to process a continuous stream or a large batch of data through a series of well-defined steps. If your problem looks like a sequence of clearly separable transformations on data, you should strongly consider this pattern. It is especially well-suited for data processing pipelines, log analysis systems, audio and video processing workflows, compiler design, real-time analytics platforms, and machine learning data preparation tasks. On the other hand, if your system needs complex interaction between many components, frequent access to shared state, or real-time two-way communication, you would likely want to consider other architectural patterns instead, or combine this pattern with others. Let us do a quick recap of everything we have covered. The pipe and filter architecture is a design pattern where data flows through a series of independent processing steps, called filters, connected by channels, called pipes. Each filter has a single responsibility. It receives input, does its job, and produces output for the next step. Filters do not know or care about each other. They are completely independent. We saw this pattern in action in email processing pipelines, UNIX command line tools, and ETL data pipelines used by major technology companies. The main strengths of this pattern are its modularity, reusability, flexibility, scalability, and ease of testing. Its main limitations are the overhead between filters, challenges with shared state, and the fact that it is best suited for linear data flows rather than highly interactive systems. Architecture patterns like pipe and filter are not just academic concepts. They are the invisible scaffolding behind the software you use every single day. Understanding them gives you a new lens to see how complex systems are built, and it gives you powerful tools to design better systems yourself. Whether you are building a small personal project or designing a large-scale enterprise system, knowing when and how to apply, this pattern can make your software cleaner, more maintainable, and far easier to scale. If you found this video helpful, please give it a like and consider subscribing so you do not miss our upcoming videos on other architecture patterns like event-driven architecture, microservices, and the model view controller pattern. Drop your questions or thoughts in the comments below. We read every single one, and we would love to hear from you. Until next time, keep learning, keep building, and keep asking why things work the way they do. Thank you for watching.